Hello, everyone, and welcome back from that awesome session with Danielle, Michaela, and Sarah. I hope you learned lots about growth secrets from Thriving Practices. Get ready now for an inspiring session with Dr. Kara Fitzgerald, all about epigenetics, biological age clocks, and beyond. Dr. Fitzgerald is actively engaged in clinical research on epigenetics and longevity using a diet and lifestyle intervention. Developed in her research and practice, she has published 2 clinical studies on the potential bioage reversing effects of an 8-week DNA methylation supportive diet and lifestyle in middle-aged men and women in the journal Aging. Dr. Fitzgerald is on faculty at IFM, is an IFM certified practitioner, and lectures globally on functional medicine, longevity, and epigenetics to practitioners and consumers. She maintains an award-nominated podcast series, New Frontiers in Functional Medicine, and an active blog on her website, drfitzgerald.com. Her clinical practice, the New Frontiers Functional Medicine and Nutrition Clinic, is located in Newtown, Connecticut. In this session, Dr. Fitzgerald will cover the current state of epigenetic biological age clocks and their applications in clinical practice, the most appropriate and affordable biological age measurements for clinical practice, evidence-based nutrition and lifestyle interventions that influence both gene expression and epigenetic aging. Dr. Fitzgerald, I will hand it over for you to take it away.
Hi, everybody. Okay, I am on stage, but from what I understand, you're not able to see my slides in presenter mode. Let me see if I can get them into presenter mode and have this work. How about now? Tell me you can see them in presenter mode, folks.
It looks like it's still in the other mode, not yet presenter.
I am so sorry. I'm not entirely sure what to do. I'm in presenter mode here. I'm so sorry.
Yeah, maybe if you want to share a different Chrome tab and it'll switch to the presenter mode. If not, I think it's fine to even just have it all up, make it zoom in a little bit more, and then we can see the slides a bit better.
Okay. All right, folks. Really, my apologies on this. I'm going to share my screen and pop my slides up just as the entire deck. And then I'm going to walk through them. So you're seeing them as the deck?
Yes, we can see it as the deck right now. And zoom in and we'll try to make the most of it.
Can you see that I've just zoomed in on it?
Yeah. Yes, we can see that.
Yeah, we'll make the most of it. And then I will make this available to you so that you can, so you can hand them out to the attendees and they'll be able to move through these themselves. Okay, so let me start the talk. I wanted to give just a little overview on epigenetics. I know a lot of you are really quite versed in epigenetics at this point. It's been a huge topic of conversation in the functional medicine space. But briefly, the field of epigenetics is really studying all the biochemical interactions and structural interactions with DNA. So you can see the DNA, if you were on slide 3 now, you can see DNA. It's wound around histones, those little blue wheels, if you can see those guys. And then there's all sorts of little biochemical activities that happen. One of the key biochemical activities, and I should say all of this activity, all of this complexity that is the field of epigenetics, influences what genes are on and what genes are off. This is incredibly important. There's a continuum of this activity. So we can change gene expression incredibly rapidly, or we can turn genes off and control the behavior of genetics over a lifetime. So for example, different epigenetic marks, including DNA methylation, will allow a liver cell to remain a liver cell to remain a liver cell over the course of the individual's life. Whereas on the other hand, if we're exposed to pollution in the environment, epigenetics, DNA methylation in specific, but other marks as well, will change rapidly to allow our DNA to produce proteins to respond to that toxic assault. So there's this a continuum of exposure. DNA methylation, slide 4, is where I've been doing a lot of my research. That's one of the most rigorous and lasting marks. So again, it can respond quickly, but it's also a key player in keeping that liver cell a liver cell over the course of the life of the individual.
Hey, Dr. Kara, I've got your slides on. So if you could stop sharing your slides, I can get it in full screen mode right away.
Okay.
Perfect. All right, let's continue. Thanks so much.
All right, keep going. I see the title slide. So why don't you keep going? Okay, keep one more slide. Okay, there we are. So DNA methylation is an area of research we can do. Thanks, Mary. Thanks for that applause. We can use DNA methylation now. We can test biological age in clinical practice. When I first started studying, it was limited to the research setting, but it's evolved, and our ability to really look at DNA methylation and to look at gene expression has expanded to an extraordinary extent. One of the things that is very clear is that DNA methylation patterns in youth look different than DNA methylation patterns as we age. Next slide. And interestingly, so there's this predictable change to DNA methylation patterns. And as we age, those methylation patterns actually look similar to different disease states. For example, the cancer microenvironment looks eerily like an aging methylome. Next slide. In a variety of ways. So if we zero in on the tumor microenvironment, we'll see that hypermethylation is happening. So good genes that we want on are being turned off. And then bad genes, the so-called oncogenes that promote cancer, these are on. So this is the tumor microenvironment. And when you look at the aging microenvironment, we see something similar, the aging methylome. In youth, however, we don't see that same kind of pattern. Okay, next slide. Again, the cancer microenvironment looks like the aging microenvironment. Next slide. We see this disordered methylation on the aging journey really across disease processes. Next slide. And as a result, everybody, aging itself really dominates the disease risk for the diseases of aging. So as we age, the risk of developing heart disease, cancer, COVID, dementia, diabetes, et cetera, rises meteorically. So there's this predictable change that's happening in the methylome and elsewhere in the body that really allows these things to, to increase in risk. Next slide. How can we change it? How can we allow the health span to catch up with the lifespan? So, we have in fact increased the lifespan with different sort of heroic interventions, drugs, and so forth. But the health span has not been in lockstep. So those diseases, the aforementioned diseases, we're just really at risk of getting. Next slide. Lifespan has increased, but again, health span has not. Next slide. And some of these countries are actually doing extremely well, like Japan, for instance. Because the aging journey is so incredibly predictable, we can measure it using DNA methylation. So again, those patterns are very predictable over time. And we've created a whole suite of clocks that to varying degrees can measure the aging phenomena. They can measure, and predict youth, infancy, even, you can even have a negative age. They've taken in utero specimen and clocked it in the negatives, and then of course positive on up to centenarians. We can reliably predict the ages of centenarians. Next slide. The cool thing about these DNA methylation clocks is they're actually better predictors of time to illness and time to death than is chronological age alone. Next slide. Next slide. So clocks have evolved. We're on to third generation clocks. They're getting more and more and more sophisticated at being able to really perceive the aging phenomena and then allow us to enact interventions to tweak it and then retest relatively quickly to see whether our interventions are working. Currently in our clinic and in our research practice, we are using a third generation clock, and it's called the pace of aging. So this doesn't give you an age, a numerical age value that is hopefully younger than your chronological age. This provides the rate at which somebody is aging. So if you're aging at a rate of 1, you're aging consistent with your chronological age. If you're aging greater than 1, your age is accelerating, your biological age is accelerating. So you really want to be less than 1. Next slide. There's a lot of conversation happening right now regarding whether we're actually reversing age or are we slowing it down. It's interesting. We're being a little bit more careful in our languaging of what we're doing with regards to changing epigenetic age. So when you look in our research papers, we talk about reversing it or the potential of reversing it, but it may be more appropriate to say we're slowing it down. And then we also want to be specific that what we're doing is changing the epigenetic clocks. Next slide. Now, this aging phenomena is happening across mammals, again, in this very predictable way, so predictable that Steve Horvath and his colleagues, Steve is the inventor of really the whole field of epigenetic clocks. He started it, and he's still hard at work on it, and he's developed this pan-mammalian clock that can measure the rate of aging in mammals. So there's shared methylation patterns across mammals that are consistent. Next slide. And this makes us think about aging, the journey, the process of aging, which is so predictable. It's so predictable we can measure it, not just in humans, but in mammals, as possibly being something that's coded into our epigenome. So yes, we know lifestyle insults, the exposome will influence the rate of aging, but there's also probably something pre-programmed in there that's consistent across mammals and dictates life expectancy. So in humans right now, we're looking at 120. In Greenland sharks, they're living to 450. In fact, I don't think they reach sexual maturity until about 150 years. Next slide. Vittorio Sebastiano, a scientist out of Stanford University, suggests, go back. Yeah. So he says that the epigenome is hierarchically dominant over all of the other hallmarks of aging. So all of the other ways that we investigate and measure aging, in his research, epigenetics sits at top. And if you reprogram the epigenome, you really have this potential to reverse all of the hallmarks and therefore really turn back the hands of aging time. It's pretty extraordinary. So in his world, he would not be in the controversy of whether we're slowing or reversing aging. He's clear that we are in fact reprogramming the epigenome and then therefore reprogramming aging, and there is a reversal phenomena. So it's an interesting little background debate happening in in the world of science. And I have some podcasts. If anybody listens to my podcast, this conversation is being featured in a handful of conversations I've had recently. Next slide. So again, here are the hallmarks of aging. In our work as functional medicine clinicians, we're entering into the conversation here in a variety of different ways. We're thinking about dysbiosis, we're thinking about inflammation, et cetera, et cetera. What Sebastiano argues is that if we really can put some energy around epigenetics and changing it, we have the chance to influence the course of all of those other hallmarks. Next slide. And he has, in fact, this is a clock out of his laboratory that proves what he said. So using this clock, when it's changed, they can see all of those downstream hallmarks of aging change as well. This is a very exciting clock, and one that I hope is clinically available to us in the not so distant future. Right now, it's only in the research setting. So let me just be super clear. The clocks that we use now, if we're measuring biological age in clinical practice, are surrogate markers of the aging phenomena, most likely. But what Sebastiano and his group are starting to show that if we change the structure of this clock, that we're actually reprogramming epigenetics, and changing this clock will show the influence on the downstream hallmarks of aging. And really, perhaps it's capturing the aging journey more effectively than any tool to date. Next slide. But we need to have them easy, and we need to be able to do this in clinical setting. His clock is not available. So what are we doing? Next slide. Next slide. Next slide. We're using the pace of aging. Yeah, keep going. Next slide. Next slide. We're also using something called the PhenoAge calculator. The PhenoAge calculator is a really easy tool. You can see the link down there at the bottom. We make this available to everybody for free. You can grab a simple biochemistry, standard blood chemistry. So this is a chem screen and a CBC plus a CRP. So you can access those. You can plug it into the calculator, and you can get a biological age calculated using this tool. Next slide. I'll show you an image of the spreadsheet. So here it is. And this is the foundation of what another DNA methylation clock was built on. So this is a pretty cool, easy, affordable clock that really kind of mimics a DNA methylation clock. Next slide. We also have a free biological age quiz that you can access. There's the link there. We built this quiz for people to, freely use in the clinic setting, for people to take and then take again after making, lifestyle changes and dietary changes. One of the really cool things we discovered with this, so we built it based on the best science at the time. Next slide. One of the awesome things we demonstrated is that our quiz actually correlates significantly with the Dunedin pace of aging clock that I just referenced earlier. It also correlates with telomere length as well. So, more than just a pop quiz fun to take, we're starting to stack a little bit of evidence for its utility and for it correlating with some of these cool DNA methylation tools, and it's absolutely free. Next slide. All right, a little bit about beyond the clocks. DNA methylation, yes, it's a phenomena that allows us to capture what's happening with regard to aging, but there's a heck of a lot more going on in the methylome, a heck of a lot more. And my entry into thinking about epigenetics as a functional medicine clinician was thinking specifically about the fact that the cancer microenvironment is really dictated by changes to the epigenome. And my question as a clinician, this is going back many years, was how can our functional medicine interventions help change that, help influence methylation, help influence epigenetic expression towards something favorable? And so I was specifically interested in tumor suppressor genes because they become hypermethylated as we age. They become hypermethylated in the cancer microenvironment, and they allow cancer to really flourish. So a cool test and technology that's available now is something called GRAIL. There's actually this is a lab. There's a handful of laboratories now measuring evidence for very early cancer activity, looking at DNA methylation patterns in cell-free DNA in circulation. So this is a blood specimen. There's actually a stool test that can help give insight into colorectal cancer, very, very early. I don't think at this point it replaces a colonoscopy, but the point is DNA methylation patterns in the tumor microenvironment are incredibly predictable. And by looking at them early on, we have the opportunity to gain insight into many, many, many different cancer activities way before standard diagnostics will demonstrate activity. So this is a way that we can use DNA methylation now. Go ahead and go to the next slide. Janine LaSalle is an extraordinary scientist out of University of California in Davis, and she has mapped out the placental methylome. And let me tell you that we will be using this kind of information in our clinical practice in the not so distant future. A few things that she's pointed out, first of all, is the essentiality of folate in the first trimester. And she can see the influence of it on the placental methylome and birth outcomes. The ravages of toxins in early pregnancy. But she's also shown the incidence, the connection between the development of autism and brain activity. So the placental brain axis is something that she's mapped out. And her promise, her thought is that we will be able to look at these changes during pregnancy. So we'll be able to sample mom's blood, and in that we'll be able to pick up the placental methylome activity and distinguish information, be able to glean information on what's happening with the developing fetus that we can then correct. The promise is extraordinary. These tools are exciting. Keep going. Keep going. Keep going. What else did I want? I wanted to say something about that. Moshe Saf. So Moshe Saf is a mentor of mine, and he's one of the most extraordinary epigeneticists, really one of the first epigeneticists. He was publishing in this space long before it was appreciated as it is now. And he was on my podcast in 2017 talking about the promise of these early diagnostics using DNA methylation and being able to correct them before there was any clinical evidence. So before autism is diagnosed, before the baby's even born. So back in 2017, Dr. Moshe Saf was predicting this, and it's extraordinary to me now that we're getting closer and closer with Janine LaSalle's work. It's very exciting. I just want to turn a little bit of attention to our intervention. So eating for optimal DNA methylation expression, eating and living for optimal DNA methylation expression. This is what we developed. We called it the methylation diet and lifestyle back in the day. After we published and I wrote a book about it, it was rebranded Younger You, but it's really this DNA methylation diet and lifestyle program that we've been using in clinical practice and that we continue to research. And we designed a dietary pattern, if you're familiar with our intervention, where every forkful is all epinutrients. In fact, if I wasn't on such a timeline here, I would pop my my salad open and share it. Actually, you know what? If anybody wants to see, I did post it on stories today. My epinutrient dense leftover salad that I brought into my office this morning. So every single forkful has the opportunity to provide information to really massage DNA methylation expression towards something favorable. Going back to the tumor suppressor genes that we see in aging, that we see in cancer, that the GRAIL test is leaning on, we know that these nutrients have the potential to influence re-expression of those tumor suppressor genes. And that's very exciting to me. Next slide. This is our intervention, as you're probably familiar with. So very specific diet. By the way, it's about 3 grams of polyphenols per day, just from the diet alone. And then we have an additional polyphenol dense greens powder. There's the lowdown. These are the target nutrients. And then there's exercise and meditation and so forth. Next slide. We are currently drilling down into teasing out the elements of the dietary pattern for what did the heavy lift on changing biological age. So in our research, we showed, our group, the intervention group, became over 3 years younger, epigenetically younger as compared to the control group, or we slowed aging by over 3 years, depending on what language you want to use. Anyway, when we drill down into the elements of the diet that really did the heavy lifting, it seems to be what we call methylation adaptogens, those dense polyphenol foods. Next slide. Incidentally, in this analysis that's in peer review right now, so you'll have access to this article soon, and you can read exactly what we found. We do report that there was a significant weight loss noted in our study group as compared to control, and we didn't report that in the initial paper, which we should have. There's other studies out there looking at polyphenol dense interventions and DNA methylation expression. The Direct Plus trial is one of those. Next slide. There were 2 studies predating ours demonstrating reversing epigenetic clock, the TRIM study and then the vitamin D study. These are awesome, interesting studies. And the 2019 TRIM study was led by Dr. Greg Fay. I've got an awesome podcast with him that we just released about a month ago. If you're interested in, a nice conversation about what it is they were doing and what they're up to now as they continue to work on that intervention. That intervention is very different than ours. It used growth hormone and metformin as the main lifts in the intervention, also DHA, vitamin D, and zinc. But they show regeneration of the thymus gland, which is just so fascinating, and an immunorejuvenation as well. So check out the podcast if you'd like to learn a little bit more about what they're up to over there in the TRIM research. Here's our first study publication. Next slide. And then we followed up with a case series in women that you may be familiar with. Both of these, if you haven't seen them, are free full text. Next slide. Adherence, by the way, in both interventions was not 100%. It was very, very good, but it wasn't 100%. So we are, we're happy to see that you can move the needle on epigenetics without being perfect. The human element is allowed. Next slide. Netmind, a UK group, just recently did our intervention. There's where you can access the write-up. The link is there, and just a very small group of 4, but they adhered to the intervention impeccably, and they did slow their pace of aging. Next slide. One of the interesting things that happened in this group is they all became vitamin D deficient. In our original cohort, we allowed people coming into the study who were on vitamin D, we allowed them to continue. And we appreciate now from the Netmind cohort that vitamin D probably needs to be an intervention for those individuals doing the Younger You program who are D deficient. So that is going to be a change to our research going forward, where vitamin D will likely be included in our research subjects. We know from at least 3, maybe 4 papers now that vitamin D deficiency is associated with a biological age acceleration by a variety of different measurements. So the essentiality of vitamin D is just very, very clear in the science. What's interesting to me is that these guys still responded. They were able to slow the pace of aging despite all of them developing D deficiency because they stopped their vitamin D. If they had read some of the supplementary materials, they would have known that we allowed vitamin D to continue in our original group, but that's okay. We learned a lot from that Netmind group. We are now on to an epigenome-wide association study. So we're looking at, beyond the clocks, we're looking at all of the other genes that our dietary pattern tweaked. Next slide.
Dr. Kara, so sorry. We're 10 seconds away from kind of being cut off and moving on to the next session. In these last few seconds, just letting everybody know, please check out Dr. Kara Fitzgerald's website. Getting redirected.